What is up, Algebra 2? This is Mr. Tokar, and this is a grade improvement opportunity. Make sure you get a foldable because these notes are needed to be done in completion, fully done with neatness as well as the practice problem. So how this works. If the following notes are completed alongside with the practice problems, you are eligible for a grade increase as long as it is submitted by the end of the quarter, October 26th, by the end of the day. Your notes must be neat, and the practice must be done completely and without error. If there are errors, you will be given back the sheet and asked to correct them. Once all the notes are done completely and neatly, and the practice problems are done completely without error, we will put in points into your assessment category, which will overall help your grade by the end of the quarter. So here's another opportunity for that to happen. So let's go ahead and get on with it. This is 2.2, operations with complex numbers continued. This is an extension. We are using imaginary numbers and electrical currents, which is how imaginary numbers are used in the real world. So before we begin, we have to know about the three major components of any circuit. So a circuit can have a resistor. Here's what a resistor looks like, and here is the symbol for a resistor. You'll be looking for this symbol. When you see this zigzag, you know you are talking about the resistor component. Now, what this component does is it limits or regulates, which is why it's called a resistor, the flow of an electrical current. So this slows down the flow of electrons as they travel through a wire. The resistor always represents a real number. So remember, a real number, if we want to put in some examples, a real number is something like 2, 4, 1/2, any number, fraction, or decimal that does not have the imaginary unit I is a real number. The resistor always represents a real number. The next major component is called the inductor. The inductor is signified by this curly Q. So when you see this curly Q, you know that this part of your circuit is an inductor. This component stores energy in a magnetic field. This stored energy can be released very, very quickly, almost instantaneously, and affects the flow of electrons through wires. An inductor is always a positive imaginary number. Okay, so when you see this symbol for the inductor and you see a number with the ohms next to it, you know that it represents a positive imaginary number. So something like 1I, or 4I, or 0.5I. These are all imaginary numbers because they have that imaginary unit I, and they are all positive numbers. The last major component is called a capacitor. A capacitor has these two bars. This is what the capacitor looks like in real life. This component draws energy from a battery and it stores it, and it makes electrons slow down and makes it difficult for them to flow through. A capacitor is also an imaginary number, only this time it's always a negative imaginary number. Because this makes it hard for electrons to flow through, it pushes them away, giving them a negative imaginary number. So this could be -1I, or 2I, -2I, or -0.5I. It always is a negative imaginary number. It has a negative sign out front, and it has the imaginary unit I. So to go through our three one last time, a resistor resists or regulates limits the flow of electrons, slowing them down, and it's represented by a real number. An inductor, represented with the curly Q, is always a positive imaginary number. A capacitor, represented by these two bars, is always represented by an imaginary negative number. So it has the imaginary unit I as well as the negative sign out in front. So let's look at some problems that look at electrical circuits, and these three different components. Okay. So let's look at our definitions and formulas before we go ahead and get going. Starting off, impedance. Impedance. Impedance is a measure of how hard it is for electricity to flow through a circuit. So the longer a circuit is, the more components it has, the slower or harder it is for those electrons to make a complete full circuit around. The impedance is found by adding up all the real and imaginary parts of the circuit. With the help of impedance, we can use what's called Ohm's law. Ohm's law is the voltage, the voltage is the product, so when we multiply the impedance and the current, will give us the voltage. Voltage can be found by multiplying the current by the impedance. So let's go ahead and look at our first example. Our first example, we are given an electrical circuit. So we go ahead and look at this electrical circuit. This circle here represents this circuit's voltage. To get all the way around here, we need a total of 120 volts. So there are 120 volts that run through this circuit. Okay? In this circuit, we have three components. Our first component is the ziggity-zag, which is a resistor. Okay? This is always represented by a real number, and it limits the flow of electrons. Next, we have the curly Q, and this is an inductor. An inductor stores energy in a magnetic field and can release it, and it's always represented by a positive imaginary number. And last but not least, we have our capacitor here at the bottom. A capacitor draws energy from a battery and stores it, and it makes it hard for electrons to make this jump and complete the circuit. This is always represented by a negative imaginary number. So let's start with our resistor. Here we see 7 ohms above, and we know that because it's a resistor, it is going to be the real number 7. Resistors always represent a real number. Our curly Q, our inductor, has 3 out next to it. But we know that inductors are always represented by a positive imaginary number. So we know that this 3 is a positive 3i. And last but not least, we have our capacitor down at the bottom, which is always represented with a negative imaginary number. A negative imaginary number. So this 4 is a negative 4i. So here's our circuit. We have a 120 volt circuit. We have a resistor who's represented by a real number 7. An inductor, which is a positive 3i, positive imaginary number, and our capacitor, which is a negative imaginary number, negative 4i. So let's go ahead and let's find the impedance. So we're finding how hard it is for an electron to make it through this circuit. How much is impeding it? It's trying to stop it from flowing through. So we need to add up all of our components' resistance. So we have 7 from the resistor plus negative 3i from the inductor plus negative, oh, sorry, this is supposed to be a positive 3i, plus negative 4i from the capacitor. We can simplify this. We are allowed to add together imaginary numbers because they're like terms. So our final answer for our impedance is going to be 7. Adding these together, 3 plus negative 4 is negative 1. 7 minus 1i. This is our impedance, the measure of how hard it is for electrons to flow through this entire circuit. Okay, so this is our impedance. The second question asks us to find the total voltage for each component of the circuit, and it's given that 16.8 plus 2.4i is our current. So if we go up and take a look at Ohm's law, it says the voltage is our current times the impedance. So we know our impedance. Our impedance is right up here at the top. Here is our impedance. And here is our current. So we're going to find the voltage of the resistor. So the voltage V of the resistor. So we're going to take our current. Our current is 16.8 plus 2.4i. And we're going to multiply our current by the resistor's impedance. The resistor's impedance is 7. So we're going to multiply by 7. Okay, so it looks a little strange because our 7 is back here, but we need to distribute our 7. So we're going to multiply 7 through to get our voltage for our resistor. So multiplying 7 times 16.8 is 117.6. Now we multiply 7 by 2.4i, and we get positive 16.8i. This is our voltage for our resistor. This is our voltage for our resistor. Okay, now we're going to do the same thing for the inductor. So our inductor was negative or positive 3i. So we're going to take our current, which is Ohm's law, again 16.8 plus 2.4i, and we're going to multiply this by the resistance of our inductor. Our inductor had a resistance of 3i. And just like before, we're going to distribute that 3i. And now we have to be a little more careful because we have an imaginary number. Okay, so let's start multiplying. 3i times 16.8 is 50.4. And then we have to bring the I with 50.4i. And then we need to multiply 3i by 2.4i. Here's the tricky part. We get positive 7.2 I squared. Since they both have an I, when we multiply them together, we get I squared. And we learned earlier this quarter that I squared is the same as -1. So this can be rewritten as 50.4i 7 plus 7.2 times -1. Okay, so our final answer is going to be 50.4i minus, that's -1 times 7.2, minus 7.2. Okay, now if we want to write this in the correct order, we would write -7.2 in the front, plus 50.4i, since we want our real number first. Okay, one more component to do. We have our capacitor. So our capacitor, again, our voltage can be found by taking our current, 16.8, plus 2.4i, and we're going to multiply it by -4i. That's our capacitor's resistance. Well, I should have done this in green. -4i. Okay, and again, we're going to distribute this, multiplying. This is going to tell us our voltage for our capacitor. So if we multiply 16.8 times 2.4, oh, sorry, times, not 2.4, -4, we get -67.2. Don't forget your I. Now we're going to multiply 2.4 by -4, giving us -9.6. Again, we have to be careful. I times I is I squared. Just like before, our I squared will become -1, so -67.2i minus 9.6 times -1, giving us -67.2i. Negative times a negative, positive 9.6. Writing this in the correct order, we put 9.6 out front, and then our minus 67.2i the back. So these are our voltages for each of our components. The resistor has a voltage of 117.6. The inductor has a voltage of -7.2. And the capacitor has a voltage of 9.6. So our last question asks us to check our voltage. So each component has its own voltage, which are represented by the real numbers, which I've highlighted. Since our circuit said we had a voltage of 120, then we need to check and make sure that our voltages of each component has a sum or totals up to 120. So let's double check. We have 117.6 plus -7.2 plus 9.6. When we put this in the calculator, 117.6 plus -7.2 plus 9.6 gives us a total of 120 volts on the dot. So that means our problem is all done. Okay, let's try another one. Okay, so we have our same definitions and formulas. We know our impedance is the sum of our real and imaginary parts, and our Ohm's law is still going to be our current times the impedance. So this time, if we look at our circuit, we have a 60-volt circuit, and that 60 volts can be seen right here. This time, we have a resistor, and we have a capacitor. We do not have an inductor. So using my little symbols, here is a resistor. This is a capacitor. Our resistor is always represented by a real number, so just 2. And our capacitor is always a negative imaginary number, which it looks like it is, negative I or negative 1I. To find the total impedance, we just add our resistances together. So we have 2 plus negative 1I or just minus 1I. Okay, so here is our impedance. We have no like terms, and we're done with that. Okay, now that we have our impedance, we are now asked to use Ohm's law. What is the total voltage for each component if the current is 24.12 I? So we need to first start. Our resistor is our blue. We don't have an inductor, so we can just write there isn't one. And our capacitor is our negative 1I. So we're going to multiply our current times our component's resistance. So 24 plus 12I. And we're going to multiply this by our resistor's resistance, so 2. And just like before, we're going to distribute. So this is going to be 48 plus 24I. We didn't have an inductor, so we'll go down to the capacitor. Again, we're going to take our current, 24 plus 12I. And we're going to multiply by our inductors, or our capacitor's resistance, negative 1I. So just like before, we're going to distribute, which means to multiply negative 1I. Negative 1I times 24 is negative 24I. Negative 1I times 12I is negative 12. We have to be careful. I times I squared. Our I squared becomes negative 1, so negative 24I minus 12 times negative 1. So we have negative 24I plus 12, because a negative times a negative. So reordering this, so we're just going to flip these around. We have 12 minus 24I. I want to check my voltage. My voltage was 60. So if I take my real numbers from each component, 48 and 12, we check to see if they add up to our total voltage. So we have 48 plus 12, which is in fact 60 volts. And that is your note. So this is using Ohm's law and impedance in order to find and check the voltage of a circuit using imaginary and complex numbers. So what you need to do after this is you need to go open up, get a copy of the practice, and complete all of the circuit problems. When you're finished, turn it in with your teacher. They will check each of your circuits, give you feedback. If there's any mistakes, you have to make corrections to those before you turn them in and get your grade improvement opportunity checked off. Thanks for watching. See you guys later.